The complex numbers. Every number we've seen and discussed so far in the course has been a real number. So now we're going to introduce a whole nother number set called the complex numbers that will allow us to go back and simplify a radical like the square root of negative 16. Up to this point we said there's no real number solution, and there isn't a real number solution. The answer is non-real or a complex number. So what we began by doing is we know anything negative is actually being multiplied by negative 1, so we could rewrite that as a square root of negative 1 times 16, and we could take the square root of that factor 16, which is 4, but we're still left with the square root of negative 1, and we know an even index and negative radicand, there's no real number solution. So now what we're going to do is introduce the complex numbers, which will allow us then to find this non-real solution or simplify this further. The complex number is I. I is equal to the square root of negative 1. And that's pretty much it. If you know that, a little bit of memorization, you can go through and pretty much find any complex number. So let's go ahead and do that. Look at the powers of I squared. Well, I squared is I times I. So the square root of negative 1 times the square root of negative 1, multiplying two identical square roots together, just gives you the radicand, negative 1, which notice is a real number. I squared negative 1 is simply a real number. I cubed is I times I squared, so negative 1 times the square root of negative 1, or simply negative I. I to the fourth is I squared times I squared, or in other words, negative 1 times negative 1, which gives us positive 1, another real number. I to the fifth is I times I to the fourth. So I times 1 is simply I. And what you're going to notice is this is a four-number pattern. Every power of I will simplify to either I, negative 1, negative I, or positive 1. Where only I and I cubed or negative I are the complex numbers. In order to illustrate that, let's look at an example here. I to the 23rd. Once again, every power of I will simplify to one of those four values, I, negative 1, negative I, or positive 1. In order to figure that out, what we're going to do is simply divide i's exponent, 23, by 4. We don't care how many times 4 goes in the 23. What we're interested in is the remainder. So the remainder, when 23 is divided by 4, is 3. So I to the 23rd is equal to I to the third, and the way we write I to the third is simply equal to negative 1. Excuse me, negative I. Example 2, I to the 89th is going to simplify to one of those four possible values. So divide that exponent, 89, by 4, and to determine the remainder. The remainder is simply 1, so I to the first power, or I. So the powers of I, understand all the possible values, there's only a handful of them, but it allows us once again to simplify radicals like the square root of 16. As we just did a few minutes ago, we were able to simplify it this far, 4 times the square root of negative 1, but now that we know how to simplify what the square root of negative 1 is equal to I, we simply write it as 4i, and anytime you see that I, you know the number, or know the answer is going to be an imaginary complex number. For instance, number 4, square root of negative 80. Up to this point, no real number solution with that even index, negative radicand. But we break it up. We know negative is actually negative 1. 80 we're going to rewrite as 5 times 16. So now the square root of negative 1 is I. We can't do anything with that square root of 5. And the square root of 16, of course, is 4. So 4i times the square root of 5, which is technically the correct answer, but I is treated like a variable. And the correct way to write imaginary numbers is in the form a plus bi, where I will always be the last thing in the term, the last factor written. So the correct way to write this would be 4 square root of 5 times I. Therefore, I is the last factor written in that term. Number 5, cube root of square root of negative 72. Well, in this case, we've always been able to simplify a radical like this. Yes, the radicand is negative, but the index is odd. So we can certainly write that as negative 1 times 8 times 9, allowing us to take the cube root of negative 1, which is negative 1, the cube root of 8, which is 2. We can't do anything with the cube root of 9, so it remains exactly where it's at. Negative 2 times the cube root of 9. And number 6, just practice using properties of I. Remember, it basically has all the properties of a variable. So no equal sign, we're not solving anything, still simplifying. We cannot simplify anything inside the set of parentheses. But if you look inside each, you of course have an I in one of those terms, but the other term doesn't have an I. So we said we always write complex numbers in the form a plus bi, where a, the constant or number out in front, is a real number. If it doesn't have I, it's a real number. If there's an imaginary or complex number, that's always written second. So the real number followed by the imaginary complex number, which of course you can't combine them, they're not like terms, so nothing to simplify inside the parentheses. No exponents, no multiplication, division. So all we're doing is combining like terms, distribute that negative, negative 4 minus 2i, and combine like terms. Of course, your real numbers are like terms, and your imaginary complex numbers are like terms. So the final simplified answer, 1 minus 11i, in the form, as we see, a plus bi. A is equal to 1, b is equal to negative 11, and of course I. Number 7, multiplying two radicals, what we're asked to do. Well, we know in order to multiply radicals, we need to simplify each first. So the first one, square root of negative 28. Break that up into negative 1 times 4 times 7, which gives us 2 times the square root of 7 times I. Second radical, square root of negative 7, is simply the square root of 7 times I. So now that they're simplified, multiplying together, 2 square root of 7 times the square root of 7 leaves us just 7, and of course I times I squared. So 14i squared, but we're still not done. I squared, as we know, is equal to negative 1, so we never leave an I squared in our answer. We're always going to substitute a negative 1 in for it, which in this case gives us negative 14. Number 8, 2 minus 3i squared, so a real number, imaginary number inside the set of parentheses in the form a plus bi, being squared, so of course more than one term raised to a power. We know we need to expand that out and FOIL. It gives us 4 minus 6i minus another 6i plus 9i squared. So combine like terms, and also simplifying that I squared we just said is actually equal to negative 1. So 9 times negative 1, that last term becomes a negative 9, or it becomes a real number, so we combine it with that 4. Negative 5 minus 12i is the way the answer needs to be written. Our real number followed by imaginary complex number. Number 9, 7i times 12i. So remember, treat it like a variable. These complex numbers i's gives us 84i squared, which simplifies to negative 84. Number 10, 7 minus 6i divided by negative 2i. Well, keeping in mind imaginary complex numbers, we always need the real and complex numbers separated in the form a plus bi. So begin by doing that. 2 terms in the numerator, 1 term in the denominator. We can rewrite each term in the numerator over that denominator, negative 2i. Giving us 7 over negative 2i plus negative 6i over negative 2i, and simplify. Negative 7 over 2i plus 3. So 3 is obviously the real number. We're going to pull it out in front. So 3 minus 7 over 2i. But we're not quite done yet. We know I is a radical. I is equal to the square root of negative 1. So right now having I in the denominator means we have a radical in the denominator, which we know we can never have. So we need to rationalize the denominators, get rid of that I down there. And we're pretty much going to do it the same way as we've already discussed. Whether there's 1 term or 2 terms in the denominator. If there's 1 term, simply multiply the numerator and denominator by I, which in this case is going to give us 7i. The denominator, 2i squared, And we know I squared is equal to negative 1, so that becomes negative 2. So minus a negative becomes plus 3 plus 7 halves I is the correct simplified form for this problem. The real number 3, the value for b, 7 halves, and of course I, a plus bi. So let's look at another problem. Rationalize the denominator. 2 over 5i, so one term in the denominator. Notice that I down there, so multiply the numerator and denominator by I gives us 2i over 5i squared, or 2i over negative 5. And number 12, two terms in the denominator. One of them, of course, has that radical, so it doesn't matter whether there's one radical or they're both radicals. The fact that there's two terms in the denominator, we use the same steps as we discussed before. We'll multiply the numerator and denominator by the conjugate. So the conjugate of the denominator, 5 plus 3i, which gives us 20 plus 12i. The denominator, of course, needs to be FOILed. It becomes 25 plus 15i minus 15i minus 9i squared, which then simplifies to 25 minus 9 times a negative 1, or 25 plus 9, since I squared is equal to negative 1. So that denominator simplifies to 34. Now we see I, everything's combined into one fraction, so once again we need to separate the real numbers by the imaginary or complex numbers. And simplify then 10 over 17 plus 6 over 17i. The final simplified answer in the form a plus bi.